Hey there, and welcome to my video on programming in C. I'm really excited to take you through this assignment which I have put together as a part of my coursework at CMR University. My name is Punya Shribiyam and my university registration number is 24PPTCD077. Yep, that's how they officially identify us. This assignment is part of a course called Programming in C, and honestly, it's been quite a ride learning the basics of coding through this language. C might seem a bit old school at first, but once you start getting the hang of it, you realize how powerful and logical it really is. A big thank you to Dr. Nagracholi, our faculty for this subject, who has helped us to understand just how to write code, but why the logic behind it matters. His way of teaching has really made a real difference in how I think about solving problems. The course code is 4CSPL1112, which probably doesn't mean much to anyone outside class, but for us, it marks the beginning of our coding journey. In this video, I'll walk you through the different parts of my assignment. I'll try to explain things in a simple and clear way, especially if you're someone who has just started out or curious about what C programming is all about. Alright, let's get into the heart of this presentation: data structures made easy, a beginner's guide. Now, I know the term data structures might sound a bit technical or even intimidating at first. I remember feeling the same way when I heard it for the first time. But here's the good news. Once you understand what they are and why they matter, everything starts to make a lot more sense. So let's break it down. At the most basic level, a data structure is just a way of organizing and storing data. Imagine you are a computer. Your computer is a super organized person. When you give it information like a list of names, some numbers, or even files, it wants to store them in a way that it makes it easy to access, update, and process that information later. Think about your phone's contact list. That's data structure. It organizes names, numbers, and maybe even photos in a format where you can scroll through, search, or sort alphabetically. Another example is your to-do list app, where tasks may be organized by priority, due date, or category. That's all powered by data structures behind the scenes. In programming, data structures helps us to manage all this in logical, efficient way. They let us write code that's not just functional but also optimized and easy to maintain. If you don't use the right data structure, your program might still work, but it could be slow, messy, or unnecessarily complicated. Now, there are many different types of data structures, each serving its own purposes. Some of the basic ones include arrays. These are like shelves in the cupboard. Each shelf has a number and you can store one item in each. They are great for storing fixed size lists of elements. Linked lists. Imagine a treasure map where each clue leads to the next location. Linked list works similarly. Each item points to the next. Stacks. Think of a stack of plates. Last one in, first one out. That's exactly how this data structure works. Queues. These are more like a line at a ticket counter. First come, first served. Trees and graphs. These are a bit more advanced but very powerful for handling hierarchical or network data, like file systems or social networks. Now, you might be wondering, why do we need so many different structures? Well, just like you wouldn't use a spoon to cut a pizza, you shouldn't use a stack when queue is a better fit. Each structure is optimized for certain types of tasks. Some are great for searching, some for easy insertion, others for memory efficiency. In this video, I'll be walking you through some of these core structures in more detail, with examples and simple explanations, so even if you're brand new to programming, you will be able to follow along. The goal here is not just to memorize definitions, but to understand how the structures work in real life and when to use which one. So buckle up and get ready because we are about to make data structures not just easy to understand but actually fun to explore. Well, let's start with the important question. What exactly are data structures? Think of data structures are different ways to organize information, like putting your books on a shelf, your clothes in a closet, or your snacks in a different jars. Just like we organize things in our daily life to keep things neat and easy to find, computers also need to organize data. And they do that using something called data structures. Let's break it down. First, the definition. A data structure is simply an organized format to store and manage data. That's it. Imagine you have a box of Legos. A data structure is like the container that holds them and tells you how they are arranged by color, size, or shape. Now, why do we care about organizing data this way? That brings us to the purpose. Data structures helps computers access and update information efficiently. In real life, if you throw all your clothes into one big pile, you'll spend hours finding your favorite t-shirt. But if your clothes are folded neatly and sorted, you'll find it in seconds. Similarly, good data structures save computers a lot of time and effort. And finally, the importance. Data structures are foundational for all programming and software development. Whether you are building a simple app or a huge website like Amazon or Instagram, behind the scenes, data structures are silently doing all the hard work, managing users, storing photos, handling messages, and even more. So, if you are learning programming, think of data structures as your superpower. They may seem a little tricky at first, but once you understand them, you will be able to write code that faster, smarter, and more efficient. In the next slides, we will explore different types of data structures, each with its own special use, kind of like different types of containers for different jobs. But don't worry, we will take it slow and keep it fun. Now that we know what data structures are, the next question is, why do they even matter? Well, data structures are like the hidden heroes of computer programs. We don't always see them, but they do the heavy lifting behind the scenes. Let's explore four big reasons why they are super important, and I'll explain each one with simple real life examples so you never forget them. Efficiency. Faster data access saves time. Let's start with efficiency. Imagine you are in a library. One version of library just throws all the books in a huge pile on the floor. The other one has shelves, labels, and an index. Which one do you think will help you find a book faster? Well, of course, you choose the one which is well organized, right? Exactly, the organized one. That's exactly what data structures do. They make data easy and quick to find. If your program needs to search through a huge amount of data, like finding a specific contact in your phone or checking your past orders on Amazon, a good data structure can reduce the time from minutes to milliseconds. Efficiency means your app runs faster, uses less power, and feels smoother to the user. In programming, time is precious, and efficient data structures save a lot of time. Organization keeps data neat and easy to find. Next up is organization. Think of your wardrobe again. If you just dump all your clothes into one drawer, find socks becomes a daily adventure, right? But if you organize them, shirts in one place, jeans in another, socks in third, suddenly everything is easy to find. In the same way, when we use the right data structure, We are not just dumping data, we are organizing it smartly. This is helpful for both computer and for the programmer, whether it's sorting exam marks, arranging files, or managing users in an app. Keeping data neat makes everything easier to handle. Problem solving, the right structure makes the job easier. Now, this one's a big problem solving. Let's say you are building an app that tracks buses in a city. You need to update locations, manage routes, and answer questions like which bus is closest to me right now. The way you choose to store this data, like whether to use arrays, linked lists, trees, or graphs, affects how fast and easy it is to solve these problems. Think of it like choosing tools in a toolbox. You don't use a hammer to tighten a screw, right tool for the right job. Similarly, in programming, choosing the right data structure can make your solution elegant, fast, and reliable. It's like having superpowers while solving a coding problem. Memory use optimizes how memory is used. And finally, here is our memory use. Memory is like space in your backup. You want to fit in everything you need, but you also want to use the space wisely. Let's say you are building a mobile app for a low end phone. You can't just use an unlimited memory, you have to be smart about how you store data. The wrong data structure may waste space or even crash the app. The right one, on the other hand, will fit the data perfectly, no more, no less, and will work smoothly even with limited resources. So, by choosing data structures wisely, we not only make programs faster but also make sure they run well on all kind of devices. Now, wrapping it all together, so let's quickly summarize why do data structures matter. They make programs faster and that's our efficiency. They keep data clean and manageable, that's our organization. They help solving problems in right way, problem solving, and they use memory smartly, memory usage. Whether you are designing a chat app or a shopping site, a video game, or even AI, data structures are the heart of everything. And here's the cool part, once you understand them, you will start to see them everywhere, not just in code, but even in how you organize your own life. Alright, let's talk about one of the easiest and most commonly used data structures, the array. So, what exactly is an array? Think of an array is like an egg carton. You have a row of boxes and each box can hold one egg. In programming, each box is a container for data and all the boxes are stuck together in a row. Each item in an array is placed at a specific position which we call an index. This index starts from 0, so the first item is at position 0, the second at 1, the third at second, the fourth is at third, and so on. Well, let's say we have an array that holds the number of students in 5 classes. Over here, it's in square brackets and enclosed with commas like of 30, 25, 28, 31, and 27. Over here, 30 is at index 0 and 25 is at index 1. 28 is at index 2. This means if you want to know how many students are in class 3, we can go directly to index 2, no need to search from the beginning. That's what makes arrays powerful. They give us direct access to data using numeric positions. You can think of arrays as the most basic toolbox every programmer uses for simple, neat, and very fast. Avoid mixing data types. It is important to note that all elements in an array must be of the same data type. This means you cannot mix different types of values like integers and floating point numbers in the same array. As the example I'm showing here, you can use in my array open close, which is equals to from bracket 25 comma, you can normally use the parenthesis as well, but majorly the flower bracket 25 comma 50 comma 75 comma 3.15 comma 5.99 close and a semicolon. Pause the video for some time and check it for yourself what the result you got. In the example above, the value 3.15 and 5.99 will be like to 3 and 5. In some cases, it might also result in an error. So it is important to always make sure the elements in the array are of the same data type. So we'll execute this. Yes, few times we do get errors, so make sure that we commonly and generally use the same kind of data types. Now let's get into array size, or we can call it as length. To get the size of an array, you can use the size of operator. Well, I'm so sorry I can't type and execute now because I got some issues while transferring the file, but I've shown you the program in the screen and well as output, so we'll discuss about it. So if you saw here, int my numbers open close equals to 10, 25, 50, 75 and 100. Printf and size of my numbers, as you can see, we gave it normally. Well, we got our output as 20. Like usually it's supposed to be 5, but here it's just 20. 5 elements, so it's supposed to print 5, but it gave 20. Why? It's because the size of operator returns the size of a type in bytes. You learned in data types that int type is actually of 4 bytes. So from this example, we can tell like 4 bytes into 5 elements, which is equal to 20 bytes. Knowing the memory size of an array is great when you are working with large programs that require good memory management. And still, when you just want to find out how many elements an array has, you can use the following formula, which divides the size of the array by the size of the first element in the array. Let's discuss about making better loops in array. In the array loop section in the previous chapter, we wrote the size of the array, the loop conditions. This is not ideal since it will only work for array for specified size. However, by using size of formula from the above example, we can now make loops that work for arrays of any size which are more sustainable. As I've written, you can see here, in my numbers, you have declared your numbers 25, 50, 75 and 100. You initialize, int I, then you have given the for loop, then we have given our print thing. So if we execute that, we got our array elements. Well, let's speak about real life examples of array. So to demonstrate a practical example of using arrays, let's create a program that calculates the average of different ages. So here I given an array storing different ages has int ages 20, 22, 18, 35, 48, 26, 87 and 70. Well, we gave a float, average sum is equals to 0, we initialized it, we gave int I, and next we give int length. We are getting the length of the array, size of ages by size of ages enclosed with 0, which is like an index. Then we got a loop through the elements of the array, we used our for loop, and at the next time average is equals to sum divided by the length. We giving the calculate the average by dividing the sum of the length, and now we are printing the average. So over there it's 40.75 is the average age. And when we look into this program, this finds the lowest age among different ages. So let's take an array storing different ages like 20, 22, 18, 35, 48, 26, 87 and 70. We took our int I, and we are getting the length of an array with int length is equals to size of ages by size of length. and we are creating a variable and assigning the first array element of ages to it. Well, like int lowest age is equals to age of 0. Now we are taking our loop through the elements of the ages array to find the lowest ages. We took for loop and if, and here is our executed code. So let's dive into see multidimensional arrays. So in the previous chapter you learned about like arrays, which is known as a single dimensional arrays. These are great and something like you will use a lot in programming in C. However, if you want to store data in a tabular form like a table and with rows and columns, you need to get familiar with multidimensional arrays. A multidimensional array is basically an array of arrays. Arrays can have another number of dimensions, and in this thing we gonna introduce the most common two-dimensional array. A two-dimensional array is also known as a matrix, a table of rows and columns. To create a two-dimensional array of integers, take a look at different following examples. Well, we'll dive in directly to the axis of the elements of two-dimensional array. As you can see on the screen, to access an element of two-dimensional array, you must specify the index number of both the rows and columns. This statement accesses the value of the element in the first row 0 and the third column 2 of the matrix. So if you try this, you're gonna get output 2. And remember that if array indexes starts with 0, 0 is the first element, 1 is the second element, and so on, etc. If you want to change the elements into dimensional arrays, you can change the value of an element referred to the index number of the element in each of the dimensions. Like you can just take first row as 0 and the first column as 0. Try yourself and make sure you get the right answer. So now let's go to the loop through a two-dimensional array. To loop through a dimensional array, a multidimensional array, you need one loop for each of the array's dimensions. The following example outputs all elements in matrix array. Let's take any int matrix 2, 3, 1, 4, 5, 3. We are just separating them with curly braces so that you can understand it very easily. And we are taking our int I and j. We took our for loop and we got our output as 1, 4, 2, 3, 6, 8. It just printed the same way how we arrange in an array. Well, we have a linked list, chain of elements, node creation, linking nodes, insertion and deletion, and traversal. We'll know each of them in detail in other slides. Node creation. Let's begin with the building block of a linked list, the node. Imagine a node like a train compartment. It carries two things, the data and a link to the next compartment. This link is like a chain that connects the compartments. In C programming, we define node using struct. One part stores the actual data like a number or a name. The second part is a pointer. It points to the next node in the list. Think of it like this. If your data is 5, the pointer tells you, hey, the next piece of data is over here. Here's a simple snippet for a node. Struct node end data, struct node pointer next. We can create a node dynamically using malloc, which allows us to allocate memory during runtime. This makes linked list more flexible than arrays because you don't need to know how many elements you'll have in advance. So in real world terms, every time a new passenger joins the train, we add another compartment. No need to worry about pre-booking and all the compartments. Next is the linking nodes. Now let's talk about linking nodes. This is how we build the actual chain. Once we have our train compartment nodes, we connect them using pointers. Each node's pointer leads to the next node and so on. For example, node 1 leads to next, which is equals to node 2, and node 2 leads to the next, which is equals to node 3, as already I have shown in the screen. It's like giving directions. Node 1 says go to node 2 and node 2 says go to node 3. The last node, however, has no text, so it points to null. That's how we know we have reached the end of the list. This linking gives us one of the major benefits of linked list. Dynamic structure, we can grow or shrunk the list as needed, and every node only needs to know where the next one is. This is very different from arrays where every element lives next to each other in memory. Here nodes can live anywhere. We just keep track using the links. Now we'll use the traversal. Let's explore how we move through a linked list. This is called traversal. Imagine you are exploring a scavenger hunt where each clue leads you to the next one. You start at the head of the list, the first node, and follow the pointers from node to node. This continues until you reach a node that says pointer is null. In C, traversal might look like this. Struct node pointer temp is equals to head. Well, temp is not equal to null. Then you give your print statement and temp statement. This prints out each data value in the list. But here's something you have to remember. Traversal in a singly linked list only gives forward. If you want to go backward, you need a double linked list where each node points both the ways. So think of single linked list like one-way street. You can move forward but not back. Well, insertion and deletion. Finally, let's look at how we insert and delete nodes. This is where linked lists really shine. Imagine you're adding a new train compartment. Easy. You just adjust a few connections, same goes for removal. To insert a node, you find the position, create the new node, and update pointers on the new node fits in the chain. Here's an example. New node connect to the next, which is equals to the current next to the next. Current connected to the next, which is equal to your new node. Deletion works in reverse. You skip the node to the deleted by chancing the previous node pointers to point to the one after the deleted node. Then you are free from the memory. Well, like previous next is equals to delete to the next, free to delete. No need to shift every element like in an array. It's like taking out a compartment and connecting the remaining one directly, quick and smooth. This flexibility is what makes linked list a go-to choose when you are dealing with a dynamic number of elements like playlist, management apps, memory managers, or even undo, redo operations in software. Fine, let's wrap up whatever we have discussed right now. So there you have it. We create nodes to hold data and links. We link them into a chain. We traverse the chain to access the elements. We traverse the chain to access the elements. And we insert or delete nodes without much fuss. That's the beauty of linked list, like flexibility, efficiency, and dynamic. Well, moving on forward to the next slide, here is our quiz, which is kind of an overview in short, like arrays and linked list. Well, which structure has a fixed size? And the answer is array, as we discussed before. Which uses pointers to link elements? Well, it's linked list we recently discussed. Which allows easy element removal? It's linked list we discussed earlier. Right? Perfect. Stacks and queues, which are fundamental linear data structures to turn into like any form of data into a better form. We will dive deep into it. Understanding stacks, push and pop operations, understanding queues, enqueue and dequeue operations, uses cases and comparisons, and let's wrap it everything in detail. Well, we'll start with the stack, last in, first out, which we even call as LIFO. It's a simple yet powerful concept. Imagine a stack of plates. You keep adding new plates on top, and when you need one, you remove the topmost plate first. This is known as LIFO, last in, first out. The last item you added is the first one to be removed. It's like the pile of books or undo operation in a text editor. Each change is pushed on top of the stack and you undo them in reverse order. In C, we can implement a stack using an array or a linked list. Here is a basic question. Hashtag define size 100 int stack of size and int top is equals to -1. The variable top tells us where the last item is. When we push, we increase top. When we pop, we decrease it. The key idea, we interact only with the top. No picking at the middle. Let's go to the push and pop operations. Now let's explore like core operations of push and pop. Push means adding an element on top of the stack. Pop means removing the top element. It's like stacking states and unstacking them. Only the top chair is accessible. Here is how a push might look in code. Void push, int value, if loop, print, return. As you can see on the screen, I'm just reading briefly stack plus top and how pop works. Pop works like int pop, if loop, print, return, then again return stack. Notice the error checks, like you'll definitely get errors because overflow when the stack is full, underflow when it's empty. This helps build intuition stacks having capacity limits and respecting them is crucial. Let's go to the queues. Queues is another linear structure but with a different order. FIFO, first in, first out. Imagine people standing out in a line for a movie tickets. The first person in line is served first. Queues are everywhere. Print jobs, customer service calls, task scheduling. In C, a queue can be implemented with an array like this. Define size, enqueue size in front, rear. Front. Front points to the first element, rear points to the last inserted element. Just like in real life, we add at the rear and remove from the front. Now let's talk about the heart of queue operations, enqueue and dequeue operations. Enqueue means adding an element at the rear. Dequeue means removing the element from the front. Think of a bus queue. People enter at the back and leave from the front. Here's how enqueue might look. Void enqueue, end value, if statement, printf, return, if again queue, and dequeue, in dequeue, if loop, printf, return again. Well, just like with stacks, we check for overflow and underflow. There's also a smarter version called circular queue. It wraps around the array for better memory use. We can talk about that in other sessions if possible. So uses and comparisons, so we understand like why do we need, right? Uses of stacks, we can use it for the expression evaluation, converting infix to postfix, and recursion function calling, handling, syntax parsing. Use cases of queues: CPU tasks, scheduling, print spooling, breadth first search, BFS in trees and graphs. In summary, we can wrap it like stacks and queues both store elements linearly, but the order of operation is what sets them apart. Stacks, LIFO, only the top is active, queue, FIFO, like a real world line. You will use both often, whether in coding, interviews, or real world applications. Understanding their mechanism builds a solid foundation for advanced data structures. Alright, let's now dive into something you already experience in your daily life, but maybe not realized it. It's called queue. Not the kind of skip in the cafeteria, but the structure behind many apps and services and even more playlists. Let's explore like how queues work both in real life and in programming. What is a queue? Like everyday analog. Imagine standing in a line at a movie theater. You buy the ticket only when your turn comes. First come, first serve, as I mentioned earlier. That's how queue works. The first person to enter the line, the first one to leave. That's why we call FIFO, first in, first out. Queues are all around us. You open your favorite music app and hit play next, song, queue up. Your order food, your request joins the queue. Printers, they queue up your documents. It's fair, predictable system. Enqueue, adding to the queue. Now let's break this down. When a new person joins the line, they go to the rear. In code, we call enqueue, E-N-Q-U-E-U-E. So, when data or tasks come in, they are added to the next of the queue, just like a new person joining the back of the line. Let's say we are building a ticket system. When 5 users request tickets, they are adding to the queue one by one from the rear. And queuing, waiting in a line. Once something is enqueued, it just waits, like you waiting for your turn at doctor's office. Now jumping ahead, no skipping, everything is based on the order in which it was added. This waiting phase is what we call queuing, and this concept is very powerful. In fact, operating systems use queues to manage which programs get CPU time, central processing unit time. Have you ever noticed your phone slowing down when multiple apps are open? That's because they are completing in a queue to get processed. Dequeue, removing from the queue. Now it's your turn, you have served and you leave the line. In a queue, that's called dequeue. The first element that was added is the first to be removed. Let's go back to our example. Say we enqueue task A, B and C in that order. When we dequeue, A goes first, then B, then C. And why not from the middle? Because queues are not built for random access like arrays. They are designed for fair processing, not speed or indexing. Why use K like queues?
real world tech examples. So why do we even use queues in programming? Here are just few examples you can hear out, like customer support chat boots. Each user messages enters a queue to be processed. Print jobs, multiple users sending documents to be shared printer. Order processing systems, e-commerce websites place each new order in a queue. Task schedulers, background tasks are lined up for CPUs to execute them one by one. These examples shows us like that queues are not just theory, they are how order and fairness are maintained in real systems. Well, we'll give a real visual recap. Let's recap with a simple visual flow. Enqueue, add item at the rear, queuing, wait your turn, dequeue, remove item from the front, and this process keep looping. Just like you waiting for your turn at concert, a bag counter, or even for your food delivery to arrive. Limits and variations like these circular queues. One last point before we move on, standard queues work linearly, but in advanced scenarios, we use something called circular queues to reuse space efficiently. That's something we will get to later in this series. So that's queues in a nutshell. Simple in concept, powerful in action. Coming up next, we'll explore much more about like how these gonna be used, practiced, and all. Let's look into deeper like how stacks and queues order matters much more detail, so you'll not forget. And I'm repeating it again and again, so it is much clearer. So stack analog, plate stacked, last in, first out, LIFO. Use, undo actions, browser history. Queue, analog, line at checkout, first in, first out, FIFO. Use, task scheduling, print jobs. Imagine you are in a massive library with millions of books. How do you find the one you need quickly? You could wander a side by side or use the catalog system, which points you straight to the right shelf. In computer science, trees and hash tables are like the catalog system. They help programmers or programs organize and retrieve data at lightning speed. Today we will explore how these structures work, why they are so efficient, and why they show up in real life. From your phone's contact to the video game AI. Hierarchical trees are like nature's blueprint for data. What are trees? Let's think what are trees. Picture a family tree. Your grandparents are at the top, their children branch out below, and so on. In computing, a tree works the same way. Nodes hold data like names in a family tree, edges connect parent nodes to the children, the root is the topmost node where everything begins. Analog, think of a decision tree in Choose Your Own Adventure book. Each choice leads to new branch, just like data branching in tree structures. Types of trees. Not all trees are alike. Let's meet two key types like binary trees. Each parent has at most two children, left and right. Example, a quiz where every answer has yes or no. Each choice splits the path. Binary search trees. Supercharged for search. Left children are smaller than the parent, right children are larger. Real world use, your phone's contact list is likely stored in BST for fast name lookup. Ever noticed how apps like Spotify find songs in milliseconds? Its binary search trees help make that possible. Now, balancing act now. What if one branch of the tree grows away longer than the others? Searching becomes slow like a librarian checking every shelf randomly. So, balanced trees, example like AVL or red-black trees, automatically adjust their shape to keep searching faster. Well, like a gardener pruning a tree to ensure even growth and easy fruit picking. Let's go to hash tables, the speed demands, like speed demands. How hash tables really work. So now imagine a magic mailbox. Every letter's data has a unique address key. No searching, just go straight to the slot. That's a hash table. Key value paste, your key, example a friend's name, points to a value, their phone number, hash function. This magic formula converts keys into address. When you save a contact like Alice 5551234, your phone hashes Alice to find where to store the number. Why so fast? Because hash tables aim for time complexity. Near instant lookup no matter how much data you have. But how? The hash function spreads data even across buckets. Collisions, two keys hashing to the same slot, are rare but handled gracefully. When it comes to the real world time, websites use hash tables to track your session data. When you log in, they hash your session ID to fetch your profile instantly. And trade like when we go for the trade-offs, hash tables aren't perfect. They use more memory to minimize collisions. Unlike trees, they don't store data in order. It's like stuffing socks into a drawer by color, fast to grab, but good luck finding a matching pair alphabetically. So, when should you use? Let's compare. Scenario: need to store some data, then you have to use BSDs are ordered, keys are scattered when it comes to hashtag. Priority on speed, tree are logarithmic time, hash table are near instant. Memory constraints, tree are compact, hash table are extra space for buckets. So, database often use B trees, a tree variant for indexing, while Python dictionary in hash table optimized for speed. So let's wrap everything what we have studied now, from your phone contacts to Amazon product catalog. Trees and hash tables silently power the tech we rely on. Next time you search for a song or log into an app, remember there is an elegant data structure working behind the scenes. Which structure would you use to build a spell checker? Why? Let's discuss. Fine guys, we are almost nearer tips to start learning data structures. So I understand data structures are very important, really important. So begin with basics, understand each type's purpose and use of it, and use real life analogs so that you can relate the topics to daily objects. And make sure you practice coding with small examples, and why not you try with simple problems with array and something like lists, and ask yourself a lot of questions, use forms and study groups. Have a good learning. So let's do a quick recap of everything what we have learned from this long, and what are the next steps you can take further. So first, mainly understand the concepts. That's really important before you stepping into something, before you solving a problem, before you gonna experiment on something. Understand the concept. Basic of 6 key data structures, as I have mentioned earlier, very clearly, and apply to problems. Whatever the concepts you have learned, make sure you apply that to your problems. Use analogs to grasp use cases. That makes it even more simpler. And try to practice coding. When it comes to coding, practice is everything. It's not just smartworks and all how people refer to, but in coding, practice everything, right? And test simple programs. Start with the simple programs, don't go with the complex. That would just mess up everything. So just go with simple test programs where that build up the confidence within you, and you can go even more bigger and keep exploring. Don't stop there, keep exploring, build on your knowledge step by step ahead every day. Well, we are at the end page of the slide. Thank you for learning with me, and just know you people all are amazing. Thank you for joining me on this data structures adventure. Whether you're coding newbie or a seasoned programmer, I'm so grateful you took the time to watch, learn and geek out with me. Your support means the world. Every like, comment and subscribe help this channel grow. Let's keep making tech fun and accessible together. Stay connected, subscribe so you never miss a listen. Join the discussion in the comments. I would love to hear what topics you want me to tell next time. Follow me. Everybody good. And remember, even the most complex algorithms start with a single line of code and sprinkle of patience. Thank you.